So our next talk is from Rebecca McElroy, and she's going to be talking to us about the observability of merger signatures in galaxy pair simulations. So Rebecca, you can share your slides and get started when you're ready.
Thank you. I will, oh goodness, my cat has decided to join us.
Excellent.
Hi, Charlie, please. Down there. Okay, so hopefully you can see this, and I will hit play. Can you still see the correct thing?
We can, yeah.
Awesome, fabulous. Okay, firstly, thanks so much for giving me the opportunity to talk today. My name is Rebecca McElroy. I'm a postdoc at the University of Sydney, where I work with Scott Kroom. And today I'm going to talk to you about observing galaxy mergers in the Fire2 simulations. This is work that I've been doing with Jorge Moreno, Connor Botchell, and Man Hani, and a lot of this was their work as well. So firstly, we want to be able to detect galaxy mergers because they're very important in galaxy evolution, and we want to be able to detect them in large surveys to understand how they impact galaxy evolution. Usually mergers are easily identified by their visual signatures, as you can see in the image on this slide. Things such as tidal tails, irregular looking morphologies, the presence of a companion, or alternatively, you can use kinematics and look for things like irregular rotation or kinematically decoupled components. You can either do this by yourself, which can be time consuming, or using an algorithm. There are various, and they have varying levels of success. So the reason we started doing this work is because I was working during my PhD on a survey of nearby AGN observed with the Muse IFU, and we were looking for evidence of mergers to see if that was correlated with the brightness of the AGN. So we looked for disruption in the stellar kinematics, which are a better indicator of the overall gravitational potential of the system than gas. And we found that despite the fact that a lot of these galaxies look visually disturbed, as you can see, particularly like the third one down from the bottom on the left, the kinematics actually remain surprisingly regular. So we wanted to investigate why this is. So the varied and transient nature of these signatures make detecting it often difficult. And in an ideal world, what we would want is to just watch a merger happen so we could see all of the stages and figure out what's going on. Unfortunately, they take billions of years and we don't have that kind of time on our postdoc contracts. So simulations allow us to solve this problem and access the time domain. So in this work, I've been using the Fire2 simulations, which I'll show this video, which will hopefully play for you. And what we have here is the gas surface density, velocity, and dispersion, and then the stellar surface density, velocity, and dispersion throughout a single merging event. So these are non-cosmological zoom-in simulations of a central and a satellite galaxy with a fixed mass ratio of 2.5 to 1. They're gas-rich spirals, and we observe them at 4 viewing angles, and we have 3 configurations of the alignments of the disks, and also varied impact parameters to see how that plays into it as well. And we also have a control suite to go along with this. So the question that we want to answer is what fraction of the time throughout a merger can we actually detect that it's happening with our observations? How often do we actually measure kinematic asymmetry? Can we use imaging to improve things? And will the field of view size of our observations have an impact on this? So in order to test this, this is just a snapshot from 2 of the simulations. We're going to use 3 fields of view. The first will be equivalent to, at an arbitrary redshift that we've placed this at, a SAMI-sized field, a Hector-sized field, and a Muse-sized field. So what we do for the kinematics that we get from the simulations, which often look a bit like this, as you can see, a bit messy, we use the kinemetry software, which was developed by Davor Krajinovic, which produces a circular and higher order model of the kinematics, which results in a full model. Focusing on those higher order models, the messier the kinematics are, the more difficult it is for the software to model, which means that we get more power in this higher order model. We then measure a kinematic asymmetry, which is based on how much power there is in this higher order model. And that means that a high velocity asymmetry means it's more disturbed and more likely a merger. In the imaging, we take the imaging from the processing of the simulations through a fake telescope, and we rotate it by 180 degrees, like so. We then minus that from the original image. And the greater difference between the images means that it's less symmetrical or more asymmetrical. And so we measure this photometric asymmetry, which is how much power is in this residual image. We note that we keep the field of view the same. We don't use those 3 fields of view because we assume that we're using like an all sky survey or something similar. So what this really gives us is we can measure these 2 properties versus time, which is something you can't do in the real world. So what we've got here is we have simulation, separation on the y-axis and time throughout the simulation on the x-axis. The 3 colored areas are highlighted and are the pair phase, which is when it's a pair of galaxies, so 2 galaxies. The merging phase, which is while they're like starting to coalesce, and the post-coalescence phase is after coalescence has occurred, so they don't get any further away from each other at that point. So we can plot our velocity asymmetry as a function of normalized time and look at how it varies in these 3 phases. As you expect, you see higher asymmetry just after the galaxies pass each other for the first time, so that's at first passage over here and at second passage, and then kind of consistently high through the coalescence. You see something similar in the photometric asymmetry. Again, you have a peak after the first passage when the galaxies are close together, again at second passage, and then it starts to go down once they've coalesced, which is sort of what you expect. So using all of this, we define a criterion above which we would consider the asymmetry to be detectable in observations. And then we calculate the fraction of the sample that is above this threshold asymmetry. So using just our kinematic measurements, the fraction of the sample that is above this criterion is shown here. So we have the 3 fields of view in the 3 colors. So maybe don't worry about trying to disentangle all of this, but at the top we have the full interacting sample, and then we have the pair phase, the merging phase, and the post-coalescence phase. And I'll highlight just this top interacting part and the pair phase. And you can see that with the full field of view, we're able to detect mergers are occurring 66% of the time. But with the smallest field of view, that goes all the way down to 30%. This is even worse in the pair phase, where in the smallest field of view, we can only detect that it's actually undergoing a merger 9% of the time. However, if we throw in our imaging as well, we're able to bring these numbers way up. So we can see in the whole interacting sample, we can detect upwards of 80% all the time. And it really, really improves the pair phase because you don't lose the satellite galaxy from the field of view when you also have the imaging. So just to answer those questions that I posed in the beginning, how often do we see kinematic asymmetry? If we just use kinematics, we see in 66% of our full merging sample are detectably asymmetric, which would imply a 2/3 detection rate in observations. How much does field of view size matter? Turns out a lot. This rate is significantly impacted by the field of view size, and if you're only using kinematics and a small field of view, you may detect as few as 9% of pair galaxies undergoing a merger. Can we use our imaging to improve the detection rate? The answer is yes, very much so. And what fraction of the time throughout a merger can we observationally detect that is happening? By combining our kinematic and photometric measures of asymmetry, we dramatically improve our detection rate, particularly of pairs in the smallest field of view, from 9% all the way up to 78%. So in conclusion, we can detect mergers using IFUs with smaller field of views, but we need large-scale photometry in addition to accurately detect the mergers in every phase. So still to come on this work, we need to look in more detail at the different phases of the merger and how the asymmetry can evolve within those. we also look at the different alignments of the disk and how that impacts things. And we also look at the effect of viewing angle, so what angle the simulations are observed from. And we're also going to compare this to observations. So keep your eyes peeled for the paper on this. It should hopefully be out soon. And thank you so much for your time.
Thanks, Rebecca. That was awesome. Really interesting stuff. Lots of questions coming through in the Slack, but I'll pick a few and you can have a look later. So from Brent, we have nice talk. For the symmetry measure in the simulation, how do you define the center to rotate around?
So the simulations are always on the center of the central galaxy. Sorry, that doesn't really make sense. But the pixel 00 is always the black hole of the original galaxy. So you're always on the central, not on the other one kind of just flies around and you're always centered.
Cool, thanks. I'll just pick another one that looks fairly quick. From Esteban Jimenez, nice talk. Do your kinematic measurements depend on the mass ratio of the merger progenitors?
So I've actually only done this on the fixed mass ones. They would. I think the kinematics would vary greatly if we used a different mass ratio of mergers. So there are 3 sets of this. It's just we didn't want to overwhelm ourselves with thousands and thousands of simulations at once. So we thought we'd tackle one problem first.
Sure, that's great. Yeah, there's a lot more questions in the Slack, so just encourage you to have
Okay, I'll head over there.
Thank you.